In this video, we're going to solve the electric field due to a ring of charge. And while there is symmetry and other arguments that can simplify this particular problem, I'm going to work this problem in general to show the mathematics the student needs to do to be able to solve any problem, regardless where the point the electric field is asked for. So in this problem, I have a ring of charge, and that ring of charge has a radius r right here. And right over the center, it's in the xy plane, is a point P, and that point P is on the z-axis at a distance z. And I want to find the electric field at that point. The way to work any of these types of problems is by starting by working an infinitesimal piece of charge, writing the formula for that electric field, that infinite point of charge, and then adding up all the point charges around the ring, which if it's continuous like this, doesn't mean summing, it means integrating. So here we go. First, we start with the definition of electric field for a point charge. dE is equal to K times dQ over R squared, where R is the distance from this charge to the point I'm looking for, which is point P. And then R hat, and R hat is a unit vector pointing the direction along R. So this is R hat, this little arrow right here. Okay? Now, one of the things that makes this problem mathematically difficult for students is that this R hat is not constant direction. And that means it cannot be pulled outside of integrals like ijk. We're going to have to figure out how to rewrite it in terms of our Cartesian unit vectors in order to do the mathematics of this problem. That often involves trigonometry and coordinate changes and things that students have to be able to learn how to do to be able to work these type of problems. Now, in order to sum up these solutions all the way around this ring, we're going to have to rewrite three things in terms of the variables that we're summing. We're going to have to rewrite dq in terms of what we're summing. We're going to have to write r squared in terms of variables that we're working with, and r hat. Let's start first with dq. If we were to look on top of this thing like this, and there was a piece of charge, say our piece of charge from here, let's say to there, that charge depends on its length. And we can write that as dq is equal to the charge per length lambda times the arc length of that charge, of that piece, which is this right here. Well, that arc length depends upon the radius times the angle, which I will call phi. So this small angle is d phi, and this length here, r d phi, is the arc length ds. This is very similar to what we did in Physics 1 for rotational problems. So what I'm going to be summing over is I'm going to be changing this angle phi as I go around, stepping around, up, to add up all the little points. So that's why I need to rewrite dq. I also need to write r hat, and I need to write r squared. Well, r squared is pretty simple. R squared, I have a triangle here, and r is equal to the square root of the radius of the ring squared plus the distance z squared. That's just the Pythagorean theorem. Now we get to the harder one. We have to deal with r hat. To deal with r hat, the first thing I'm going to have to do is I'm going to have to get it into Cartesian coordinates. I want to eventually get it into, in Cartesian, but first I'm going to have to get it into cylindrical. My fault. So what I'm going to do is I'm going to draw a parallel line to this parallel line. This angle I'm going to call theta. Therefore, that angle must be theta by geometry. And in cylindrical coordinates, you'll remember there are three variables. There is phi, the angle going around. There is z, the distance along the cylinder. And there's this distance, which we don't use r because we're already using that. That usually is rho. Of course, in our case, rho is in fact equal to our big R. So r hat depends upon this side, like that, pointing along outward in the positive rho direction, and that's the opposite side, so it's sine theta rho hat. And it has an upward projection, which is adjacent to my angle, so that's plus cosine theta k hat. However, if you look here, I can actually write sine theta and cosine theta in terms of my rho and r, or if you would, my big R and r. So if I do that, I get the following. Sine, that's big R over r, rho hat. And for cosine, that's z over r, k hat. Now I need to do something with rho hat, because rho hat in cylindrical coordinates is also not constant. It can't be stuck inside of my integrals. So I'll remind you of something else. If we were in the xy plane, then this would be rho hat, and this angle there would be phi. And let me draw it a little bigger. Rho hat has a length of 1. This is phi. So this is the x direction. This is the y direction. So rho hat is equal to 1 times the adjacent. That's the cosine of phi, I hat. And then its opposite, sine phi, j hat. So now my r hat is equal to big R over little r cosine phi I hat plus big R little r sine phi j hat plus z over r k hat. And now I have it in terms of my Cartesian coordinates. So I can take this, my r, and I can plug all of these back up into dE. So let's do that. So if we do this, here's what we get. The infinitesimal electric field due to that point charge depends on K, it depends on lambda, it depends on R, and then it has a R cosine phi I hat, R sine phi j hat, and z k hat times d phi, all of this over r cubed. And now I want to replace my r using this formula here. And I get that d is equal to k lambda r over r squared plus z squared to the 3/2 times r cosine phi I hat, r sine phi j hat, and z k hat d phi. Now I need to integrate this as I vary phi all the way around the thing. So the electric field is equal to, well, k lambda r and z and r, all of that's constant. So I get k lambda r, r squared plus z squared to the 3/2. Then I have r integrate of the cosine of phi d phi, and I hat is also constant, so it can come outside, constant in direction and magnitude. That is unique to these unit vectors in Cartesian coordinates, which is why we have to get into Cartesian coordinates to do the calculus. The integration is from 0 to 2 pi as we go around the circle. The second integral has r, j hat, and integral 0 to 2 pi sine phi d phi. And the third integral has z k hat, integral 0 to 2 pi d phi. Now, this might look really nasty or such, but turns out it's really not so bad. Two of these integrals are going to be 0. There is no component electric field due to symmetry. The integral of a cosine is a sine, and the sine at 0 and at 2 pi is equal to 0. So this integral turns out to be 0. This integral ends up being the cosine of phi. But when you integrate the cosine phi, you got cosine of 2 pi 1 and cosine 0 is 1. That also turns out to be 0. This integral turns out to be 2 pi. So now we have that the electric field is equal to k lambda r times z times 2 pi times k hat over r squared plus z squared to the 3/2. So there is only an upward electric field out of this problem. Something else that we note. But if it's uniformly charged, then the total charge is equal to lambda times the circumference, which is 2 pi times r. So the electric field is equal to k, and then I take lambda times 2 pi r, and that gets me q, and z k hat over r squared plus z squared to the 3/2. Now, a couple of things to note about this. Notice that if z is positive, then the electric field points up. But if you're in the negative z direction, then the electric field points down. I'm going to come back and look at this with the binomial expansion in the next video and show you that you can see the symmetry of other things, such as if you're very far away, shouldn't this look like a point charge? If you're very close, what should it look like then? All right, we'll see you at the next video.